All right.
We'll go with it.
So does anybody have any idea what we mean by a restoring force? I guess I should have asked you, can you give me an example of something in simple harmonic motion before we started this whole thing? All right. Well, what do we think about? I guess I jumped right ahead. What do we think about when we think about something oscillating? Back and forth, back and forth. So it's a very repetitive motion. It's going on and on and on. And a restoring force is what makes it do that. In other words, you know, something as the object moves right is trying to stop it and pull it back left. And then as it starts to move left, that force turns around and starts to try to pull it back right. So we call it a restoring force because it's always trying to get the object back to like where it started, or what we would call equilibrium. So this restoring force, or the restoring torque, if we look at something that's oscillating like a pendulum, has to be proportional to displacement in order for it to be in what we call simple harmonic motion. Again, you can have tons of different kinds of oscillations and so on, but for what we're going to do here and for the solutions that we're going to present, these things are going to be true, and it's going to be simple harmonic motion. So energy is conserved, the restoring force has to be proportional to displacement, and finally the last thing that's true for anything that is in simple harmonic motion is the period. What's the period? The time for what? For one rotation, one oscillation, the time for one, one back and forth. The period, we're going to find out for everything that we do, is independent of the amplitude. So now what's the amplitude? I'm just throwing words out here like crazy. Yeah.
Isn't that like how far up and down the wave is?
Yeah, you can kind of relate it to a wave. Yeah, we're not going to talk about waves here, but it would be the maximum displacement, how far right or how far left or how far it swings right or swings left, that this thing goes. So the period is going to be independent of that. So it's not going to matter whether I move the thing, 10 centimeters to the right, 20 centimeters to the right, etc. The period will be independent of that amplitude. And we're going to spend a lot of time deriving these periods because that's one of the things they like to make you do on the AP exam. And you'll see every time we come up with a new equation for period, it never has anything to do with amplitude at all. It always just depends on some other parameters and so on. Alrighty, so what are we going to do with these? We're going to look at a mass spring system because that's one of the most common examples of simple harmonic motion. And we'll look at, again, why these things are true, and then we'll derive this. So we got a whole bunch of stuff that we're going to do. All right. I'm going to erase this. We're all set? All right. This is not a very big board, so this is going to take me some room. So let's start off with a mass spring system. So a mass spring system is nothing more than a spring with a mass, and it has to be on frictionless ground. Why does it have to be on frictionless ground? So energy is conserved, because if we had some friction there, then energy is not going to be conserved. Will we still have an oscillation? Sure, but it won't be simple harmonic motion. So what we're going to do here wouldn't apply if we had friction on there. Alrighty, so in order to get this to oscillate, I have to, right now it's just sitting here at rest. What do I have to do to get this thing to start going back and forth? I have to move it somehow, right? So I'm going to literally either pull it to the right, or I could squish it to the left, assuming the spring could be compressed. So let's just imagine I pull it a certain amplitude to the right and let it go. Describe the motion to me. What's going to happen to this thing over time? It's going to slingshot back. So if I pull it to the right, it's going to come back. Why is it going to come back? There's a restoring force. So if I drew a force diagram of it when it was over here, what would be on that force diagram? What's to the left?
Force.
What kind of force?
Restoring force.
A restoring force, and what's doing the restoring? What do we call the force that's actually making it happen? A spring force. So we would have a spring force to the left. What other forces do we have? Just because we want to have a complete force diagram. Gravity and what else? Normal. So this thing is going to start to come back. Now here's why simple harmonic motion and oscillations are a little more complicated than other types of problems. Who remembers, again, we're going to assume here that we have a linear spring. What on earth is a linear spring?
It's on a flat surface and just horizontal.
Don't think the geometry of it. Think of what this force depends on. We've all heard of Hooke's law?
Yeah.
What's Hooke's law? It's a good review, good overall review. Kx, so a linear spring obeys Hooke's law. So when we say a linear spring, we mean a spring whose force varies linearly with its position. You can have other springs. I'm sure you've seen it throughout the year where you have, they might give you an AP problem where they're like, oh, you have a spring that's, force is kx squared or kx cubed or some other function of x. Those would not be linear springs. They're varying with the squared of position or the cube of position. And we're not talking about that here. We're talking about a linear spring. So this force has got to be equal to, and usually they put Hooke's law with a negative. Why?
Opposite direction.
It's the opposite direction. When you pull this spring to the right, the force is in what direction?
Left.
To the left. If I squish the spring to the left, what direction would the force be? To the right. So they usually show that, again, it is a restoring force. It's trying to get the mass back to the middle. So this has to be a linear spring because what was one of our rules or, conditions that had to be met for a simple harmonic motion? The force had to be proportional to the displacement. So here it is. There's our evidence that that's going to be true here because this is a linear spring. As soon as I did that, this is no longer simple harmonic motion. Everything that we're going to do would not apply. So this makes it okay. We have it varying with just position. Alrighty. So again, this thing's going to end up moving back. Eventually it'll be over here. Squishing it, what would the force diagram look like over there?
Positive.
So the spring force would just be going in the other direction and gravity and normal would still be here. Alright, here's the problem and here's why this is a challenging situation to be in. Tell me about this force. As the object moves to the right, back to the middle, to the left, back to the middle, to the right, does that force stay constant? No. So what makes this problem a bigger problem is that the force is not constant. And if the force is not constant, is the acceleration constant? So then the acceleration is not constant. Which means I cannot approach this from just using standard kinematics. I can't do, a little force diagram, say F net equals ma, and then do, V equals VO plus AT, or V squared equals VO squared plus 2AX, because those equations assume that A is constant, and I clearly do not have a constant A. Now we've been in the situation before where we have a force that varies, and that was in what situation throughout the year? I don't know if we did it last time. I don't remember what we did last time. Drag force. So drag force was another situation that we found ourselves in where the force varied. And we had to come up with a whole different way to solve those problems. Again, we have that same situation here. As this object starts to move back, the force actually gets smaller, the acceleration gets smaller, and so on and so forth. So we have a problem here. So we have to, again, come up with a way to address this. How did you address it in drag force? What's that?
Something with calculus.
Something with calculus, yes. Something with calculus. So you basically had to derive the equations of motion for that object, and you had to go and set up differential equations in order to do that. Sound familiar? Yes. Same thing's going to happen here, but there's a slight twist to where we were, with drag force. So here we have the force is not constant. It varies with position. So we have to basically, we need to derive equations of motion. So we have to start from scratch, which is annoying, but that's what we have to do, because we just can't go with our kinematic equations because they only work for constant acceleration. So how do we do this in drag force? Where do we get these equations from? How do we derive these equations? Does anybody remember where we began?
Force equals mass times acceleration.
A little F net equals ma, my favorite formula in physics. So we have to start with F net equals ma. That's the only way we can get at these equations of motion. Well, what is the unbalanced force that's causing this whole thing to accelerate? It is what? The spring force. And that spring force has what value? It has our negative kx. And we can set this equal to ma. We could solve it for a and say, okay, a is negative kx over m. And that's great. We could find the acceleration for any specific position, but that's not helping us figure out what's happening over time. And that's usually the way we write our equations of motion. Everything is a function of time. Now, when it came to drag force, what did we do at this point? What's that? We changed the acceleration into a derivative. And because we had a force that varied with velocity, we changed it to a derivative that was with respect to velocity. That's not going to help us here because I have a force that varies with position. So I need to, change acceleration into a derivative associated with position. And what derivative is that going to be? The second derivative. So I know that a is just d squared x over dt squared. So I can replace it with that. And now we have, last time with drag force we had a first order differential equation. Now we have what's called a second order differential equation. And these, sadly, not as easy to solve as first order differential equations. So with drag force, what did you do to solve a first order differential equation? Anybody remember? You did integrate. You basically got, you separated the terms. In that case, you had a dv, dt. You put the dv and the v's on one side of the equation. The dt's, there usually wasn't a t, but, constants could go anywhere. Then you integrated both sides, right? Sound familiar? Mm-hmm. So here we have a second order differential equation. Again, much more complicated to solve from a calculus standpoint. So we're not even going to attempt the calculus solution, because the calculus solution to this is way beyond the calculus you need for the AP Physics exam. So how are we going to solve this thing if we're not going to use calculus? An acceptable, and my kids always love this when I go this way, an acceptable way to solve any differential equation is guess a function and see if it works. We're going to take a guess and check approach. And we're going to do this guess and check approach once today because it's going to work for everyone. So we want to just guess a function and see if we plug it in, does the second derivative with respect to time give us this? So that's, you know, again, functions could be anything. So I want to now make an educated guess. I don't want to just say, oh, well, obviously I'm going to guess that x is, you know, 3t squared minus 7t plus 4. You know, I want to make an educated guess to what this function is going to be. So to make that educated guess, because that is, again, for any differential equation, that's always an acceptable way to solve it. Of course, it could be like searching for a needle in, you know, for a needle in a haystack if you're trying to guess a solution. But again, if we can make an educated guess, it's going to make our life easier. So we have to come up with a function for position. So let's think about, what does the position of this thing do over time? Let's say that I pulled it here and I call this time 0. So where does my position start? At time 0. If I'm holding it here, ready to let go. Positive. How far? Amplitude, right? So it's going to start somewhere here at amplitude. Then what happens as time goes on? It goes from amplitude. Now where does it go back to? Right back to the middle, which we would call a position of 0. Then where does it go as time goes on? It goes the other direction. Again, with energy being conserved, it's going to go just as far to the left as it did to the right. So now we end up where? At negative a. Then where are we going to go back to? 0. And then we're going to go back to a, because as long as energy is conserved, how long is this going to go on? Forever. And all of a sudden, we can make a very good educated guess as to what the solution to this is going to be, because what's that looking like? Not a parabola. Let's hear it. All right, let's show why it's not a parabola, because as time goes on, we come back, and we go back down, and we go back up. Does that help?
It's like sine.
It's a sine curve or a cosine curve. It's some sort of sinusoidal function, because it's going to go up, come down, go back up, come back down, go back up. So the solution has got to be sinusoidal. So now I can make a very educated guess. I'm going to say that x, now I'm going to say, well, what is, okay, now put your pre-calc hats on. What is the equation of this graph? You're like, why do we learn these things in math? Why do I ever have to know how to write the equation of a sine curve? Here's an example, or a cosine curve. X equals what? Who remembers how to do this? Well, we have, what I drew is a cosine curve. Do we all agree with that? So I'm going to say it's cosine. What do we put in front out here? A, excellent. So the amplitude, the height of the graph goes out front. Now we end up with time inside, and something's got to go in front of that time. Nobody remembers their pre-calc.
No.
It had something to do with like how many waves fit into, you know, how many curves fit into 2 pi. Oh, I'm seeing maybe like a little spark of memory there.
I mean, the worst teacher.
Well, it's it basically, the number that shows up here was basically telling you how many curves fit into 2 pi radians, and so on. But we're going to give it a name, omega. So just trust me for now. That's what we're going to call it. We're going to give it this term omega, a lowercase omega. And omega is 2 pi divided by the period. So in other words, the period is the time for one cosine curve. So if the time for one cosine curve was 2 pi, then you would have 1 here, and it's telling you you fit one sine curve in that 2 pi. If it was, just pi, then it would tell you fit 2 in, so that number would be 2. Does this sound familiar at all? A little bit, right? All right, we're going to keep it as omega, but know that omega is equal to 2 pi over t, and I think this might even be on the AP formula sheet. All right, now, we have to throw one more thing in here, because this is a cosine curve because I said time 0 was where? Time 0 started when I held it here. What if it was already oscillating and I said time 0 started when it passed the midpoint? Then it would be a sine curve. So a sine curve is really just a cosine curve shifted by 90 degrees, and a cosine curve is just a sine curve shifted by 90 degrees. They're really like the same thing. So what ends up showing up in here is this little term phi. And phi is what I just call a little phase shift. So in other words, I chose what time 0 was when I chose this as a cosine function, but maybe it doesn't match up. So I may need to shift my curve. Again, I can make this cosine curve into a sine curve by just making phi what value? Really testing the pre-calc skills. Yes, 90 degrees. So if I just make that 90, the whole thing would become a sine curve. All right, so there's our very educated guess. Now, to make an educated guess, we now have to check the solution, which means we have to do what? We have to plug it in to here and see if it works. So we guessed the solution, now we have to check the solution. So I'm going to just erase this stuff over here. So now we're going to check the solution. So we're going to take that and plug it into d squared x over dt squared equals minus kx over m. Well, if I'm going to plug that into this, that means I have to take the what of it? The second derivative of it, right? Because I can't plug it into here. It's telling me I have to plug in the second derivative of that. All right, so let's go over here. So dazzle me with your calc skills now. And take the first derivative of this, because we have to take the first one before we can get to the second one. And the first derivative of this will give us what? The velocity. Awesome. So tell me what the velocity will be, and then take the second derivative of that, and that will technically give us what? One more time. The acceleration, right? Because that's what remember we took acceleration and we plugged this in for acceleration, so it makes sense that we get that back. So go ahead and try to come up with those two derivatives. And if you are not done calculus, you might struggle. But again, this is going to be, you're going to be excited if you have one of these problems, because you're never going to have to do what we're doing here again. Okay?
I know how to do the power rule.
Alrighty. Technically, well, this is like the chain rule, so you're going to have the power rule within the chain rule. No? So this is, again, sine and cosine are one of the 5 equations that you need to be able to take, 5 functions you need to be able to take the derivative of, right, on the back of your AP formula sheet. Right? Yep. All right, so what is the derivative of this? If we take the derivative of x to get v, we get what? What's the derivative of cosine?
Sine.
Negative sine, right? So we get negative sine, so we write down negative a sine. Again, we're going to just write omega t plus phi, but we kind of ignored everything in here, didn't we? So we'd have to do the chain rule. So we now take the derivative of the inside, and what do we get? Omega. So the answer here is negative a omega sine omega t plus phi. Did we all get that? Yay! Excellent. All right, let's do this again. And if we take the second derivative, now again, we did it the derivative once, now we're going to do it again. What do we get? Negative A omega cosine omega t plus phi. Again, we've ignored the inside here, so we get an omega at the end, and we get negative A omega squared cosine omega t plus phi. All right, a few things I want to point out here that before we actually plug it in, a few things that are worth noting. As we go through this. So if I'm going to erase this here right now, because we're going to squeeze these things in under here. If I plotted velocity versus time, and then I plotted, again, we're squeezing them in, but I just want to make a point here. The position versus time is going to be, the velocity function is going to be a negative sine curve. So what that means is it's going to start here, and then it's going to go, well, now I got to do this. I got to keep my things intact here. So we're going to have a negative sine curve. So we're going to start here, go down, go up, and come down, right? Because that would be the graph of this. And what would the amplitude of this be? What is this? This is my amplitude, right? So it's going to be an A omega here and a minus A omega there. Here we have a negative cosine curve, which means this one just looks like that. And again, this has the value negative A omega squared and A omega squared. All right, why I did this. I just want to point out some key things that are worth, definitely noteworthy here. All right. Where is the object when I have the maximum velocity? Where is it? What does that line up with position-wise? What's that?
0.
At 0. Why does that make sense? Why do I have the maximum velocity when this thing is right back at equilibrium? Why should the maximum velocity be there? You could argue it from an energy standpoint. You can argue it from a force standpoint. How much, let's argue it from an energy standpoint. When I'm back here at equilibrium, how much spring energy do I have? 0, which means all my energy now has to be what? Kinetic, which means I would have the maximum velocity there. So I can argue it from that energy standpoint. I also can argue it from a force standpoint. How much force do I have when I'm back at x equals 0? It's none, which means I have an acceleration of 0, which means I have to be at a maximum velocity because I'm no longer accelerating. So one thing that's worth noting here is the max v occurs at x equals 0. And then how much velocity do I have when I am at amplitude, when I'm at the edges? So when I'm here, how much velocity do I have?
0.
0. When I'm here, how much velocity do I have? 0. So why does that make sense? What's the object doing when it's all the way out here?
It needs to change direction.
It needs to change direction, and it has to do what to do that? It has to literally stop and then go backwards. So we have this v equals 0 occurs at x equals a. Another thing that's worth noting, again, some of these things are hard to remember for like multiple choice. I have now a value for that maximum velocity. It's just a omega. It's just going to be a multiplied by that 2 pi over t. That could be useful in solving problems. You never know. And so on. All right, let's just look at the acceleration. When does maximum acceleration occur? So I have maximum acceleration here, here. Where am I position-wise? Am I at equilibrium or am I at amplitude here? Here I go back to my position graph. I'm at amplitude. Here I'm at amplitude. So the maximum acceleration occurs at amplitude, when these things are at the extremes. Why does that make sense? What causes the acceleration? The spring force. And the spring force depends on what? Position. And when is the position the biggest? When I'm at amplitude. So I have to have the biggest force and therefore the biggest A. And when do I have no acceleration? So here's no acceleration, go up to here. Up, we're right at x equals 0. Here's no acceleration. We're right at x equals 0. So the A equals 0 occurs at x equals 0. Again, we're back at equilibrium. There is no spring force when we're not stretched at all, so I can't have any acceleration. These things are just kind of good to know for, multiple choice kinds of questions where they give you, a graph or something and ask you when this happens, that happens, and so on. So just keep that in mind. All right, so I just wanted to point those things out that come up from graphing these two things. All right, we need to do our guess and check. So we've guessed, now we need to check. So what are we plugging in for d squared x over dt squared? We have to plug in all of that. So we have minus a omega squared cosine omega t plus phi. All right, good. And what are we going to plug in for x? We have to plug in. Oh, I erased our original guess. So whatever we had for our original x, right, which was just a cosine omega t plus phi, right? That was our original guess. So now let's simplify this. Does this solution work? So look how nice the cosines cancel. So that's really nice. Both the a's are gone, so the a canceled. The negatives cancel. So this solution will only work when what is true? This solution works if the omega squared is the same as k over m, right? I just said there's something called omega. I don't know what the value is. But now I know that if this solution is going to work, that omega squared has to be k over m. Because if this omega squared happened to be equal to k over m, then I would have, left side equals right side, and I have a solution that, solves my equation. So this is what has to be true. So what can I say now? My answer for this is x equals a cosine. Well, now I'm not going to plug in omega anymore because I know what omega is. Omega is what? Just the square root of k over m t plus phi. And now I have a solution. Now let's see why we're never... Go ahead.
Would it need to be the square root?
Oh, yes, thank you. The square root of k over m. Let's see why I never have to do this again. Let's get back. Oh, I like gigantic boards. Let's get back. What's that?
Mr. Parker should only get board.
I like gigantic. I can never have a big enough board. My board is not that much bigger. I might have like to here. But like if I could have like, have you ever been to like a college? Have you visited where they have like the board that slides up? I would be in my glory if I had that. But and then you'd have another board behind it. But anyway, I would love to have lots of board space. All right, let's see why we're never going to have to do this again. What was our original equation that we got from our F equals ma? So from F equals ma, we got the equation what? What did we get? Negative kx equals ma, and we wrote this back as negative kx equals m d squared x over dt squared. If I wrote this and I put everything on one, or if I just isolate basically the second derivative like I did before, I had d squared x over dt squared equals, well, the way I usually do it in class is I bring everything to one side. Let's do this. So let's divide by m, and then let's bring it all to one side. So that's really the differential equation we just solved, right? I just wrote it with everything on one side. Look at this k over m. It shows up in the differential equation that we started with. So once we get to this point, we can now say, because we've gone through this whole guess or check solution, that whatever turns up right here in front of this variable to the first power is going to be your omega squared. And once you know that, you can jump from here to this solution by just plugging in the square root of that. Do you follow that? We're going to do some examples. So what's going to end up happening, the way the AP problems usually go, and we'll look at some as we go through the morning, is they'll ask you to write the differential equation that you could use to solve, but don't solve it. And then they'll say something like, using similarities to a mass spring system, or they'll just basically say, give the solution. They won't make you show how you got the solution. They'll just say, what is the solution to the equation? And they won't say derive the solution or calculate the solution, where you would have to show all that guess and check. All they would ever do is ask you to go from here right to here. Because this, a cosine omega t plus phi is going to work for any type of simple harmonic motion, whether we have a mass on a spring, a pendulum swinging, this funky thing that I brought, it's going to work every single time. And we're going to do some problems to practice it. So again, this one works for what? The mass spring system that we started with. So this is only true for a mass spring system. Now, what they do often ask you, though, is once you've got this or this, they'll ask you to come up with an expression for the period. They'll say, gee, well, derive an equation for the period of this thing. And how are we going to do that? Remember, what did we say this omega was equal to earlier? 2 pi over t, and t happens to be the period. So to find the period, recall that omega equals 2 pi over t. But we just found out what omega is for this very specific mass spring system. And what did we decide omega was? We decided omega was the square root of k over m. Couldn't I set omega equal to omega and find an expression for my period? Yes, right? So if you're going to find the period, all you do to find the period, here, we'll erase this now. All you do to find the period is set omega equal to omega. One is going to be the whole pre-calc version of what omega is. It's just 2 pi divided by the period. How many fit into, 2 pi. And the other omega you're going to have to get from your differential equation. And again, it's going to be whatever shows up in front of the variable to the first power. That's going to be omega squared. So I can set that equal to k over m, square root. So can I now write an expression for period?
Yes.
So what's my equation for the period?
2 pi over square root of km.
2 pi over square root of km, or the way you see it on the AP sheet, they just rationalize the denominator and basically bring it to the numerator, and you get 2 pi square root m over k. Does that look familiar at all? With anybody who took first year physics, maybe? Maybe, sort of. And you will find this, it's called T sub s. This equation happens to be on the AP sheet. They give you the period for a mass spring system. It is definitely worth memorizing because, you know, on multiple choice questions, they'll ask you, oh, you know, what happens to the period if you double the mass or you triple the spring constant and so on. And you have to kind of know that equation. Now, if you remember, what was one of our conditions for simple harmonic motion? I said the period was independent of what?
The amplitude?
Amplitude. Did amplitude show up here at all?
No.
No, it doesn't matter if I have a mass spring system, whether I pull it back, you know, 2 meters, assuming the spring could be stretched 2 meters, or I pull it back, you know, 2 centimeters, it's going to have the same exact period. So there it is. All right, now that's kind of a lot to take in. Yeah.
What if your spring, like, the place it's at when you're not applying force to it is 0, right?
Yeah, when the spring is in its what we call its natural state, it's not stretched or compressed, that's your equilibrium position.
So what if you could, like, stretch it super far, but you, like, couldn't compress it at all?
Then it's not going to be, you know, it's not going to be a simple harmonic motion oscillation. So it would still oscillate probably, but not. It's if it can't give you, so that spring would only be able to give you a restoring force in this direction, and it would not be able to, if it can't be compressed, won't be able to give it back to you the other way, so it would not, it would be some other kind of motion. So again, the restoring force has to be able to go both ways. Alrighty, so let's now take a look at this and apply it to a few other situations. And then maybe we'll take a break, and then we'll do a real problem and see how it goes from there. All right, so another very common simple harmonic oscillator is what we call a simple pendulum. Have you done any pendulum labs in class? Yeah? Who remembers anything about pendulums?
That's cool.
Nothing is remembered about pendulums.
It's in my brain, but I need a primer. Or, like,
All right, so we're going to start off with what we call a simple pendulum, and then we're going to do a compound pendulum, and this would fall into the category of a compound pendulum. And then we'll take a break after that. So let's deal with a simple pendulum. A simple pendulum is nothing more than like a point mass on the end of a massless string. So if you tied, you know, the best example would be if you had a, you know, one of your masses, like those brass masses you use in lab all the time. You tied it on a string and you just set it oscillating. That's a simple pendulum. We always have massless string. So here's my pendulum, and I'm going to draw it already pulled back. Yes?
We'll only have simple pendulums?
No, we will have compound pendulums as well. That's why we'll do them next. The simple pendulum, the period that we derive is also on the AP sheet. Then the compound pendulums, they're not. But we're going to show you how you can easily come up with the period of a compound pendulum as well. All right, so why does a pendulum, when I pull it to the right, swing back? Gravity, because gravity would be pointing down this way. But there is, if I look at it in this frame, there is a component of gravity that's trying to pull it backwards, right? This little component of gravity is going to make it swing back in this direction. So then when it got to all the way over here, we would then have a component of gravity that tries to pull it back the other way. Did we follow that? Now, we could do this from a force approach. It's just much easier to do pendulums and anything that oscillates through an angle. It's much easier to do them from a torque approach. We'll get the same answer whether we do the force approach or the torque approach, but I just think the torque approach is a lot easier, so we're going to go with that approach. So again, we have to do what? We have to come up with a differential equation, because as this swings downward, what happens to this component of Fg that's making it move? Does it stay this value? No, Fg itself doesn't change, but the component that's making it move along that circular path gets smaller and smaller. When we get back here to the middle, right, we would have no component. This would be our equilibrium position, right, because we'd have no component of the gravity in that, along the curved path. And then we would have it going the other way. Again, it's going to be much easier to do this from a torque approach. So instead of starting with F net equals ma, we start with what?
FG.
Well, what's the equivalent? What's Newton's second law written in rotational form?
T equals I alpha.
Net torque equals I alpha. So we're going to start from this approach instead. So we're going to give the rope a certain length L. Oh, I don't know how this, oh yeah, I did this really bad. I drew this in line with that. Instead, we'll make this longer to get our picture right.
We got you.
All right. Well, that just bothered me right now when I saw that. Okay. So let's give the pendulum length L, and we'll say that we don't call it amplitude anymore when we're talking about rotational. We'll call it theta max. So that's the maximum angle it goes through. Just like amplitude is the word we use for maximum displacement, there is no word that I know of for maximum angular displacement. I don't know if there's anything called angular amplitude. It's not something that I'm familiar with, so I call it theta max. All right, so how do we figure out torque?
Magic.
This is a good review of rotation right now. How do we calculate torque? R
force.
False.
RF sine theta or R cross F. So it's going to be RF. Well, we'll write, so we can write it all down. We'll write it's R cross F equals I alpha. And what force are we talking about here? What force is giving me the torque?
Gravity.
Gravity it is, yes. Gravity is what, again, giving me...
Why is there an X instead of sign?
Just the AP sheet writes it as torque equals R cross F, so I always start with whatever the AP sheet shows. Again, a cross product is a way to take two vectors together and multiply them and get another vector. So the AP exam, in the world of vectors, if you go on to take physics in college and higher level math, you're going to be introduced to this whole world of vectors. And they could be written like we've written them in class. Oh, you have a force at 30 degrees. Or you can write them in terms of what we call I, J, and K components. And the vector cross product, if you had your R and your F literally written in I, J, and K components, then this cross product is an actual thing you have to do with those vectors. The AP exam doesn't do the cross product, so whenever we see this, we just replace it with RFG sine theta, because that's what it is equivalent to when you have it in just, the form of the force is at a certain angle. This is the way you would do the cross product. The IJK comes out to be very helpful once you go to 3 dimensions.
Why do they do that then if they know that's not in the scope of our class?
All I can guess is because that's really the true definition of torque. And then they expect you to know that when you see it, you can replace it with RF sine theta. So,
Thank you.
so long. So RF sine theta equals I alpha. So theta here, again, so let's imagine now we're not at theta max, but we're at some other theta in between. That theta here is the same as that theta here, correct? So that theta is the angle between the R and the F, because the R goes in this direction and the F is right there, so that theta is the theta. Do we agree? All right, what are we going to replace FG with? mg, so now we can write RMG sine theta. What are we going to plug in for I? Oh, what does I stand for?
Mass
Okay, that is what, you know, I is the sum of the mr squares, or the integral of r squared dm, right? But we can think of this,
If it's a point mass.
if it's a point mass, then we know it's going to just be the equation mr squared. So we can plug in mr squared here, and we have alpha. So we're like, all right, so we're working this, right? Now we have to get the derivative in for the differential equation, and so now we're going to, instead of replace alpha, we're going to replace what? I mean, I gave it away. Instead of replacing acceleration, we're going to replace alpha. And instead of replacing it with a d squared x over dt squared, we're going to replace it with d squared. Alpha is the second derivative of angular position, which is theta. Yes, right? So we know alpha is d squared theta over dt squared. Oh, and just one more thing. Again, this is a restoring torque. So we always put these things in as negative to show that when the pendulum swings to the right, the torque is to the left. When the pendulum swings to the left, the torque is to the right. So we always put in these negative because it's a restoring torque. So we're going to plug this in. Whew, all right, so let's cancel out one of the r's. So now we have minus g sine theta equals r d squared alpha over dt squared. Did I do that right? I think so, right? I don't like... Oh, but what is r?
Radius.
The radius, and what is r based on our diagram?
Length.
Oh, so r is L based on our diagram, so let's put that in. All right, now, you should say, we have a dilemma.
We have a dilemma.
We have a dilemma, don't we? And I'm sure you're all right there with me saying the dilemma is so glaringly obvious, right? So, we can write this like we did the other one to try to come up with the omega term, right? So we can get everything, let's divide by L. So if we divide by L, that disappears, right? Let's go around here and write it all on one side of the equation. D squared theta over dt squared plus g over L sine theta equals 0. And here's the dilemma.
We use G over L.
What's that? Not g over L. We said one of the conditions for simple harmonic motion was that the force or the torque had to be proportional to the displacement or the angular displacement. So last time we had force equals kx. So force was proportional to position. What's wrong here? I don't have it proportional to theta. I have it proportional to sine theta. This is a problem.
Oh no.
It's not simple harmonic motion right now because it's not proportional to theta. And here's our way out. I don't know if you've discussed this small angle, thing and so on. If you put your calculator in radian mode and you plug in the sine of a very small angle in radians, like do sine of 0.1, I think that's probably small enough. What do you get back when you plug in sine of 0.1?
0.099.
Oh, what? 0.099. Boy, that's awful close to what? 0.1. Put in the sine of 0.05. And you get back?
0.0499.
0.049. I'm really close to 0.05.
That's cute. Are they
So
equivalent?
for very small angles, the sine of theta gives you back theta. So we're going to say, all right, we're going to do a pendulum. We're going to call it simple harmonic motion.